Hello everyone, my name is Nina Hong. I'm an applications physicist at the JA Woollam company. This presentation is about considering spectroscopic ellipsometry for roll-to-roll application. I would like to mention that this presentation couldn't be made without the help of my colleagues Jeremy van der Slice and James Hilfiger, and my collaborators Sean Garner of Corning and Professor Mark Pollix of Binghamton University. Let me start with spectroscopic ellipsometry basics and what sample properties it can measure. Unlike intensity-based optical metrology tools, spectroscopic ellipsometry measures the change in polarization of reflected or transmitted light. It is a non-destructive measurement technique for index of refraction and film thickness measurement. This illustration shows how light changes from linear polarization to elliptical polarization upon surface reflection. The polarization change comes from the different reflectance between the P and S waves. For transparent materials, the well-known Brewster's angle is where the reflectance of the P wave is 0. So ellipsometry measures the ratio between the reflection coefficients of the P and S waves. As these are complex numbers, the amplitude ratio is tangent of psi, and the phase difference is delta. These psi and delta parameters are the traditional ellipsometry measurement quantities. Spectroscopic ellipsometry, or SCE, is an indirect measurement needing a modeling or data analysis. We would first measure the sample and acquire psi and delta curves in a wide spectral range and angles. Then we would proceed with modeling based on the sample structure that we know. In this model, I assume that we already know the substrate's optical constants, which is a typical practice, and we are trying to find the film thickness and the complex refractive index. When we complete the modeling, we receive the results such as film thickness, refractive index, surface roughness, composition, crystallinity, anisotropy related parameters, or uniformity map like thickness or the index of refraction map. Ellipsometry instrumentation technology has evolved quite a bit in recent years. We can measure over 1,000 wavelengths within a fraction of a second. Using focusing lenses, we can reduce the spot size down to 25 by 60 micrometers. Some of the modern ellipsometers can measure full 16 Mueller matrix. Here, Mueller matrix is a different data type from psi delta in ellipsometry, and the Mueller matrix data type is ideal for anisotropic samples. We use SE for large area mapping, in situ or on-chamber measurement, inline measurement, or roll-to-roll application. The roll-to-roll application is what I'm specifically interested in this talk. These 3D drawings show one of our roll-to-roll ellipsometers. It features a complete control unit attached to the ellipsometer heads to avoid interfering with other cables or connectors. Now let's talk about the flexible substrates we typically encounter for the roll-to-roll applications. From the ellipsometry standpoint, there are 3 types of substrates. Metallic foils that are absorbing light at all wavelengths, flexible glass substrates that are isotropic and transparent in a wide spectral range from UV-Vs to near IR, and flexible polymer substrates that are transparent in the visible and near IR, but often these polymeric substrates are optically anisotropic. Here are the optical constants of a 40 micrometers thick stainless steel metal foil that I've measured in the past. These graphs show the typical shape of refractive index and if the extinction coefficient for metals. The absorption increase towards the long wavelengths is due to the free carrier absorption in the metal. The metal surface is often rough or scattering, which leads to slight difference in the optical constants depending on the polishing direction. The other two substrate types that we are going to deal with are transparent flexible substrate. One is isotropic and the other is anisotropic. For transparent substrates, an optical measurement may suffer from the signal contributed by the incoherent backside reflected beams. However, various methods are available to suppress them, such as using an index matching fluid or liquid, reducing the spot size, or taking care of them in the model. Flexible glass substrates are optically isotropic, which is one of the most significant advantages for simplifying ellipsometry modeling. We would measure a Cauchy dispersion shape refractive index curve in the UVVs and near IR for a flexible glass substrate. Polymeric substrates are a bit challenging due to their anisotropy. Anisotropy means the index of refraction is different in the x, y, or z directions. For anisotropic substrates, measuring their Mueller matrix ellipsometry data gives us the most accurate optical constants. And depending on the crystallinity of the polymer during the polymerization process, some polymers are close to still isotropic, as you can see from this COC optical constant, while others are highly birefringent. For example, the well-known PET or PN or polyimide substrates. For roll-to-roll applications, we can think of roughly 3 different ellipsometer system configurations. We can use transmission mode, especially for polarizing samples, such as polarizers, linear retarders, display devices, circular polarizers, or films in AR or VR devices. In this case, we are mostly interested in measuring retardance, fast axis, rotary power, ellipticity, azimuth, or degree of polarization. All of these are related to the polarizing effect of the sample. In reflection mode, we typically measure film thickness and the refractive index. If the Collimated beam systems are sensitive to the backside reflection effects, that should be taken care of in the model. And if you use the focused system, then we can separate the backside reflected beams spatially and make the analysis easier. Transmission mode ellipsometry, specifically Mueller matrix spectroscopic ellipsometry, becomes more and more popular these days. Since we measure the polarizing effect of a sample, typically this Mueller matrix, the transmission mode data analysis does not require complex modeling. The Mueller matrix itself reveals very interesting parameters such as the azimuth and ellipticity of a linear polarizer, or this wavelength dependent retardance of a linear retarder, or the circular polarizing effect of a circularly polarizing filter used in 3D eyeglasses. For the rest of this talk, I will focus on a more traditional ellipsometry example, a thin film coated on a substrate. The flexible substrates were provided by Sean Garner of Corning, and the coatings were deposited by the group headed by Professor Mark Pollix of Binghamton University. The film that I'm going to show you is a 60 nanometer thick indium gallium zinc oxide, IGZO, a semiconducting film used in various displays. I will compare the result of two different substrates, the flexible glass and a PN substrate, and the optical constants of both substrates were predetermined on bare substrates. For transparent substrates, I talked about two complexities, backside reflection and substrate anisotropy for polymeric substrates. However, if the beam size can be reduced small enough so we can avoid the backside reflections, then we can avoid both issues. The ellipsometry data psi delta for the indium gallium zinc oxide film on a glass substrate and the Mueller matrix data for the same sample on a PN substrate show this mild thickness interference pattern corresponding to the film thickness and refractive index. Here I compare the film's refractive indices on the two different substrates, and they show an excellent agreement. But sometimes adding focusing optics may not always be feasible. So if we prefer to use a collimated beam, the glass substrate sample analysis is still straightforward. All we need to worry about is how to take care of the backside reflective beams. In my result, I used the backside correction function in the data analysis software. On the other hand, for the PN substrate sample, we have to deal with a significant birefringent effect, as you see from these oscillations, as the beam travels through a long path length, which is the film thickness related, leading to a high retardance between the P and S waves. The modeling is not simple, however, as long as we have measured the accurate optical constants of the PN substrate beforehand, the modeling is doable. For this particular PN substrate, it was pre-coated with a primer layer, which I had to include in the model. I also had to fit for the orientation of the PN substrate due to its anisotropic nature. Finally, I compared the optical constants of 4 measurements, 2 different systems, and 2 different substrates. This graph shows that we can measure a reliable refractive index of the film with any of these models I just introduced. The measured film thicknesses were close to the nominal value with a slight variation. So here is the summary of my talk. Spectroscopic ellipsometry is a non-destructive thin film monitoring tool. And modern ellipsometers provide a wide spectral range and fast measurement speed, which makes them ideal for both roll or inline monitoring. Transmission mode ellipsometry measurement is useful to measure polarizing effects such as retardance, fast axis, the polarization related parameters or the polarizance. And the reflection mode ellipsometry can measure the thin film properties such as their thicknesses and the refractive index. Thank you for paying your attention to this presentation. And I also thank the SVC organization for hosting this virtual conference. And if you have any questions after this talk regarding my presentation or ellipsometry in general, please don't hesitate to contact me at nhong@jawoollam.com. Thank you very much.